team Fiat-Shamir.
Thank you. It's great to be here. Thanks for inviting me. And this talk is going to be about these strange creatures, Nash equilibrium, and this complexity zoo of problems and classes like PPAD. But the talk, basically, or the result, is a different type of application of proof systems. Here to showing hardness results. So in a nutshell, today what we're going to see is cryptographic hardness or average case, construction of average case hard problems in PPAD. If you don't know what PPAD is, don't worry, I'll tell you in a little bit. In fact, we're going to show cryptographic hardness in an even lower complexity class. These are complexity classes between P and NP, where we think problems are hard, but we don't know when we're looking for cryptographic evidence for the hardness of problems, and we'll see such cryptographic evidence today. Okay, in a nutshell, what we're going to see, and this is where proof systems come in, that we're going to see that there's a problem in these classes where solving it is as hard as breaking the soundness of a particular proof system. Okay. In particular, the proof system isn't just any old proof system that we invented, but for this crowd, a natural proof system obtained by applying the Fiat-Shamir transformation to the famous sum-check protocol, and we'll define what all of these objects are, or what some of these objects are in a little bit in the talk. But I want to start with giving you the motivation. What is PPAD? Why are we interested in cryptographic hardness of this class? I'll just mention that previously what was known in these terms is hardness based on indistinguishability obfuscation, starting with the beautiful work of Bitansky, Paneth, and Rosen, leading up to the work of Hubacek and Yogev, showing hardness within these low complexity classes. Okay, so the storyline today starts in game theory, and this fellow Nash, who posited or invented the notion of a Nash equilibrium and proved that it always exists. So we have this existence proof for a central concept in game theory. And the idea was that markets reach equilibrium, or that's the belief that's the model, at least in economics. The question is, we know these equilibria exist, but is it easy to find them? Is it easy to find them? Is it hard to find them? Can we study that from a complexity theoretic perspective? This was the contribution of Christos Papadimitriou, who embarked on kind of a systematic study of this question. And today, the stories, or what we're talking about today, is how this story interfaces with cryptography, where we also need a handsome representative. So we have Shafi. And we're going to see how crypto can shed light on the complexity of this problem that has its roots in economics, or is fundamental in economics. Okay, so what is a Nash equilibrium? I assume many of you have seen this, so let's just do it briefly. So the idea is that we have a game with two players. Both players are deciding, say, this is the famous prisoner's dilemma, where the red player and the blue player can either cooperate and then they get a certain payoff, or they can defect to the other side and then they get these payoffs. And a Nash equilibrium is a strategy profile, so a strategy for the red player and a strategy for the blue player, such that no player on his own can increase his payoff. So it's sort of a stable, that's why it's called an equilibrium. It's a stable place to be. Here, this is a Nash equilibrium. If the red player decides to cooperate, his payoff will decrease. If the blue player decides to cooperate, her payoff will decrease. The situation where both of them are defecting is an equilibrium. And notice that it's an equilibrium even though they can both do better. That's not the subject of the talk today. So that's a Nash equilibrium, and in his famous theorem, Nash showed that this might seem like a strange state of affairs. Maybe there's never such an equilibrium, but in fact, Nash showed that there's always an equilibrium. For any game that we define, an equilibrium always exists. There's always a mixed strategy, so where every player's strategy is a distribution over the possible actions. And there's always such a strategy for both players that is an equilibrium. Okay, so existence, that's beautiful. And, maybe in the real world, all of the markets and the interactions we have converge to such equilibria. It's a very nice theory. And as computer scientists, when we study this question, it's a natural question to ask, well, these objects exist, these equilibria exist, but how hard is it to find them? Is it easy? Is it hard? If we assume that the market operates, does polynomial time computations, can it really find an equilibrium? So how hard is this problem? And the first thing we might, from a pessimistic perspective, we might think is, well, maybe it's an NP-hard problem. Right? Maybe there's just no hope. Maybe there's a reduction from an NP-complete problem, like 3 coloring to this problem, and it's just hopeless. And in fact, that's unlikely to be the case. We don't believe that's the case. And this was shown by Megiddo and Papadimitriou. And basically, they looked at the, so we have our usual classes NP and P for decision problems. Similarly, when we want to compute functions, when we want to compute, actually given a game to compute its equilibrium, we're talking about functional NP and functional P, FP and FNP. So in FNP, we have complete problems like given a 3-sat formula, finding a satisfying assignment, if one exists. In FP, we have all the functions that are computable, rather than decision problems, functions that are computable in polynomial time. And in between NP and FP, we have this class TFNP, which is a class of NP problems where solutions are always guaranteed to exist. Similarly to the case for a Nash equilibrium, Nash showed that a Nash equilibrium always exists. For a 3-sat formula, it's not always guaranteed that a satisfying assignment exists. Okay, so there are problems in NP that we don't think are in TFNP, but Nash is a problem in TFNP. We have this theorem proving that for any game that we specify, there always exists a solution. And what Papadimitriou and Megiddo and Papadimitriou showed is that it's unlikely that there are any NP-hard problems in TFNP. In particular, if any problem here is NP-hard, then NP equals co-NP. The polynomial hierarchy collapses. We don't believe that's the case. So we don't think this is likely to be NP-hard. Computing a Nash equilibrium is unlikely to be NP-hard. That's the takeaway. You can think of this TFNP, by the way, as kind of a function. It's kind of hard to, it's not a precise definition, but think of it as an analog of NP intersect co-NP.
But when you talk about the mixed strategy, it involves probability. When you are going to continuous space, how do you...
Usually you discretize and you talk about approximation up to some negligible epsilon. I don't know if Elon has, or Omer has a better answer. That's my answer. I don't know if Elon is here. Or anyone else who wants to add. Well, Elon is my guru for this, for TFNP.
It's even hard to find like this, which strategies will this probability will be supported on. So that's definitely useful.
So even that's a hard problem.
What does the T stand for?
Total. And why does total mean there's always a solution? I'm not sure, but that's a terminology. Yeah. Okay, so in fact, we have this TFNP. That's a very interesting class of problems. We have Nash, which is a particular problem in TFNP. But Papadimitriou didn't stop there at TFNP. He wanted to actually find sort of more fine-grained classes or more fine-grained characterization of problems within TFNP. And in particular, he was interested in classifying these problems by the complexity of the argument that's used to show that a solution always exists. Okay, so here we have Nash's proof. That's a particular way of proving that a solution always exists. And Papadimitriou wanted to sort of systematically study these types of proof. And this led him to define the class PPAD, which is a subclass of TFNP. Okay, so it's a particular set of problems within TFNP, or between TFNP and FP. And the problem of finding a Nash equilibrium is in this class. And in fact, as we'll see, this is sort of the right class for studying the complexity of finding a Nash equilibrium. And PPAD, the definition really is syntactic. I mean, you can talk about the argument that's used to prove totality, to prove that a solution always exists. Really, the way it's defined is through a complete problem, this problem called end of the line. And PPAD is the class of all problems that can be reduced in polynomial time to the end of the line problem. That problem is just given a graph. So we're given a graph with in and out degrees 1. Okay, so every node, we have nodes in the graph. Every node has out degree at most 1 and in degree at most 1. We're given this graph. We're given a source node here in blue. And the problem is, given a source node, find a sink. So of course, if we find a sink, we know that we found it. So it does have an NP flavor. But why is it in TFNP? Because if you give me a source and the graph has in and out degree at most 1, and I start walking, eventually I have to hit a sink. Right? The only other option is that the whole graph is a cycle. But if the whole graph is a cycle, then I wouldn't have a source within degree 0. Okay, so that's sort of the intuitive argument for why a solution is guaranteed to exist. There's always a sink in this graph, and the problem is actually finding such a sink.
How do you know there's only one, is there only one source or something and one sink? Or how do you know you're not on?
No, so there may be many sources and many sinks, as is the case in this problem, and any of them would be a valid solution to the problem.
It doesn't have to be the end of the line you started on. It just
No,
has to be-
and that's very important. So the end or the beginning of any line is a solution to the problem. Similarly, with finding a Nash equilibrium, there could be many of them, and any one of them you find is a solution to the Nash problem.
So you're given one start of the line, and you could even find the start of a different line, and you would have solved the problem.
Yes. Okay, so is the problem clear? And the point is, well, if we actually look at this graph and it's in front of us, then of course it's easy to find a sink given the source, just sort of walk around or do exhaustive search. But the point is that we're interested in solving this problem on exponential size graphs. Okay? So we have a graph with 2 to the n nodes. Every node has a label, say in 0, 1 to the n. And the graph is implicitly defined. We're given functions for any node for computing its successor and its predecessor. That's the input to the problem. And now, given a source, we have to find a sink, and the exhaustive search solution will no longer be polynomial time. If you just start at a source and keep going, it might take you exponential time till you find a sink. So the question is whether given circuits or programs for computing the successor and the predecessor, and given a source, you can find another source or a sink. And now it's not clear why we would expect this problem to be in P, solvable in polynomial time. In fact, I think for any of us, for the cryptographers who have worked with obfuscation, it seems like this should be a hard problem. So that's the end of the line problem. It's sort of the complete problem around which this complexity class PPAD is defined. And Papadimitriou, in fact, showed that Nash is in PPAD. The problem of finding a Nash equilibrium is in PPAD. And in particular, there's a polynomial time reduction, given the description of a game, reducing it to an instance of the end of the line problem. So if we can solve the end of the line problem, we can find Nash equilibria. And the big open question from '94 was whether, in fact, Nash equilibria, the problem of finding a Nash equilibria is complete in this class, whether there's a reduction in the other way. And this was resolved in the beautiful work of Daskalakis et al. And then Chen and Deng, who showed a reduction in the other direction. So actually finding a Nash equilibrium is complete for this complexity class. So that brings us to the following, this view of the world. We have TF and P, we have PPAD within it, we have the end of the line problem, we have the Nash problem. These are polynomial time equivalent. We have other problems in PPAD. I think they're also complete. Right, Brouwer, and depending on how you define them, we don't have Elon. And I'm here. You are? Ah, okay. So they're also complete? Yes. Now I'm much more relaxed. Now I can stop talking and just hand over the reins.
What do we know about PPAD and TFNP?
So we think that PPAD is significantly lower than TFNP.
We know that, or we conjecture that?
We conjecture that. I don't know. Are there results along these lines? They're probably black box separations, but... Right, if P equals A, yes. But do we have any results saying it's unlikely to be the case independently of whether, assuming P is different from NP?
Yeah, all the classes are separable by oracles.
We have oracle separations, but that's the evidence we have. Okay, so we have this class. It has this very nice structure, these natural problems that are complete inside it. That seems great. And now the question is, well, it would be wonderful if we could have an algorithm for solving all of these complete problems. Right? If we could find Nash equilibria in polynomial time and solve these other problems, that would be wonderful. The intuition is that maybe it's hard, it's unlikely that we're going to get a polynomial time algorithm, but really we want evidence. And the kind of evidence we want, in fact, there are different kinds of evidence we could talk about. We could talk about worst case hardness of these problems, but really what we would want is to show that it's easy to find difficult instances for these problems. Okay, that's the intuition, and the question is how to show it, and that's where crypto can come in. And a central question since PPAD was presented is whether we can use cryptographic assumptions, so assuming problems like factoring or discrete log or learning with errors are hard, does that imply that PPAD is hard? And are these problems, in fact, in PPAD? It's a big open question. Okay, both for understanding the complexity class, for understanding these problems, and also for going to the economists and saying, well, here are actual hard instances, hard games, where we don't think a market can find an equilibrium. So that's the motivation behind the talk. And the result we'll show is along these lines. So we're going to show a hard distribution for these problems. Before going there, I just want to say a little bit, since I'm talking about TFNP and I talked about PPAD, and since I have a slide, courtesy, the slides are from Alon, and I'm sure he inherited them from various people in the audience. So I want to say, and I want to motivate this, I think there are really interesting questions here for complexity theorists, for cryptographers, for people who study proof systems. So between TFNP and FP, to Rosario's question, we have a bunch of other classes, not just PPAD and CLS, which I talked about, but other classes. We're interested, they're natural classes, we're interested in their complexity. For many of them, we know hard distributions. Okay, so assuming just the existence of a hard on average problem in NP, Hubichev, Noor, and Yogev showed that TFNP, a hard on average distribution for TFNP. For various other classes, factoring, for example, is known to be solvable in this class PPA. Collision-resistant hash functions can be broken in this class. The evidence we had so far for average case, for hard distributions, for a way to generate hard instances in PPAD is based on obfuscation and functional encryption. In this lower class, which I'm not going to define, we had evidence also, as we said, based on indistinguishability obfuscation. So these are really heavy hammers from cryptography. There are big assumptions to make. In the talk today, I want to show a different cryptographic assumption that implies hardness in these two classes. Okay? Particular soundness of a particular proof system that even the practitioners in this audience know something about.
Wait, sorry, I'm confused. So you're saying that PPP, there's a one-way permutation there?
Any one-way permutation can be inverted using a PPP oracle. Or finding an inverse to a one-way permutation is solvable in PPP. Okay.
So, but then I'm confused, because one-way permutation seems like a reasonable assumption.
Right, but PPP is a much higher complexity class, so it contains PPAD. Sorry, I should have said, these are the lower we go in this beautiful drawing, the lower the complexity classes, or sort of the weaker they are. Yeah, the harder the hardness or impossibility results.
So we don't get a one-way permutation if factoring is hard? Like there's no...
We do, so it's a more general assumption. I mean, depending on what you mean by factoring is hard. Sorry?
So factoring is in PPA.
If you can break PPA, you can break factoring. If you can break PPP, you can break also any other one-way permutation.
So you can also break factoring here, but that doesn't follow that you can break, that you can solve any PPA problem in PPP, as far as we know. Okay, so this is sort of background and motivation, this beautiful drawing. We're going to home in. I'm essentially only going to be talking about PPAD and kind of the end of the line problem in the talk today.
What does CLS stand for?
What does CLS stand for? Elon? I don't know.
Continuous local search.
Okay, so main result that I told you about today, an efficiently sampleable, so a distribution that we can sample from in polynomial time. That's in CLS or PPAD, namely meaning we can solve it in CLS or PPAD of a problem that we can solve in CLS or PPAD, and a proof that it's hard to solve randomly sampled instances from this distribution, assuming that a particular proof system is sound. And when I say sound, I mean that it's adaptively and unambiguously sound, and we'll talk about that, what that means much later in the talk. In a nutshell, assuming soundness of a proof system, we have a hard distribution on instances within these low complexity classes. And I just want to say a bit more about the proof system and the Fiat-Shamir transformation.
Sorry, can you just fill in the sentence there? You're saying...
So we have an efficiently sampleable hard distribution.
If they have one. Or you're saying...
No, we have one. That's our main result. We present an efficiently sampleable distribution that is hard, assuming Fiat-Shamir. Okay. Okay, so let's just talk for a moment about the Fiat-Shamir transformation. And then I want to say a little bit more about some corollaries of this result. So what's the proof system? It's basically the Fiat-Shamir transformation applied to an interactive proof system. And the Fiat-Shamir transformation is a popular heuristic from removing interaction from cryptographic protocols. So if we have this nice protocol, say between a prover and a verifier, has 3 messages, 3 rounds of interaction, alpha, beta, gamma. The only thing nicer than a proof system like that is one where we have less interaction. And that's what the Fiat-Shamir transformation gives us. The idea is that the verifier sends a very complicated hash function, whatever complicated means, over to the prover. And then that's used to derive the interaction, the randomness. Okay, so the prover sends the original message alpha. Beta is taken to be the hash of alpha using this hash function. And then the prover also computes gamma. And the verifier checks that it accepts alpha, beta, gamma, where beta is taken to be whatever alpha hashes to under this hash function.
The left thing is a public coin.
Yes, the left thing is a public coin. That's important. So beta is just a random, is just public randomness. Otherwise, yeah, it wouldn't be clear what to do with this compile. Thanks. So that's been hugely influential, both in terms of practice and in terms of theory. The original motivation was transforming identification schemes into public key signatures. But since then, it's been used and studied in the context of taking many message interactive proofs or protocols and converting them into 2-message. Here, we did 3 messages to 2 messages. But even if we had 5 or 7 messages, we could just keep hashing. So we always, whatever the number of messages in the original protocol, so long as all the verifier is doing is sending random coins, we can always take the verifier's message to be the hash of the transcript up to that point. So we can reduce the interaction to 2 messages no matter how many rounds we had to begin with. And the intuition is if we think of H as a truly random function, then in fact it can be shown that this transformation is sound. The big question, or the $1 million question, is whether it's sound in general, whether it's sound ever. And when I say is it sound, I don't mean whether whatever you plug in here leads to a sound protocol, but can we design hash functions for which the transformation is sound? Does there exist a hash function? Does there exist a hash function for which it's sound for a particular class of protocols? And that's been a big question in the foundations of cryptography. We had a bunch of negative evidence, or a bunch of negative results for various statements that you could, for various increasingly general statements that you could hope to make. But in recent years, we increasingly have positive answers. So we have constructions of hash functions for which it can be shown that the transformation is secure when applied to particular protocols, to rich classes of protocols, based on different cryptographic assumptions, some of them more standard, some of them less standard. And I think we'll hear more about that certainly in Alex's talk later in the week. And the question is, or what we show is that assuming that this transformation is sound for a particular protocol, the sum check protocol, which I won't get to till much later in the talk, so sorry about that, but it's a classic protocol. Assuming there exists a hash function for which the transformation of that protocol is sound, then PPAD is hard. Okay, that's the main result today. And I want to say a word about that. Even when we talk about these negative results, showing the negative results, usually what they showed is that there exist very contrived protocols for which there are no hash functions that make the transformation secure. But we don't have any results showing that the transformation, as far as I know, that the transformation is insecure when applied to a very natural protocol.
We have a result along these lines for a Kuhn's protocol in the result.
Okay, so we have one new result. We do have one result. Okay, but then the hash is contrived. Okay, so here we're talking about whether one can, so for example, take the sum check protocol. That's a concrete protocol. People here have implemented it. It's running. Take your favorite hash function, like SHA-250, 256. I would conjecture that it's secure.
You did an asymptotic version of SHA-256. It's a nice challenge for theoreticians to come up with the simplest asymptotic, like fully uniform implementation of a hash function for which you can make such a conjecture.
For which we don't know how to break it.
is both too complicated and a finite function, so you need to modify it.
The reason I bring it up is that, one of the motivations behind this talk is we actually want to generate games where it's hard to find a Nash equilibrium. And, if we can just take a proof system, applied to a simple claim, hash it with a simple hash function, and use the reduction that we'll see in the talk today to generate simple games that are hard to solve, that would be great. We're not quite there yet, but I think it's a promising direction for research. Okay, so that's the main result. I do want to say that there's been this progress on instantiating the Fiat-Shamir transformation, and in particular, that does give us a corollary. So there are assumptions under which we know how to build a hash function for which a transformation is secure, and that those assumptions would also imply that PPAD is hard. So similarly, we can generate a hard distribution on instances in PPAD, assuming the optimal security of known LWE-based fully homomorphic encryption schemes. Okay, so by optimal security, what I mean is that the probability that a quasi-polynomial time adversary, given the public key, can recover the secret key is bounded by some quasi-polynomial divided by the number of keys. So that essentially, there's no super polynomial speedup to brute force search. So a quasi-polynomial adversary can do brute force search and recover the key with this probability, and the assumption is that there's no super polynomial speedup to this attack. If you can come up with a super polynomial speedup, I think that would be really interesting news for the people who study LWE. Of course, it's not, it's a strong assumption.
Algorithms do not apply here?
No. So they would run in less than exponential time and totally recover the key, but it's not known how to run them in quasi-polynomial time and succeed with. That's an important distinction. Okay, and we also have this extra assumption that I don't want to. That's a much more reasonable assumption.
Okay.
Yeah.
So the quasi-poly here and here are just like exactly the same quasi-poly, or they're related?
No. So just the assumption is that there's no super polynomial speedup for quasi-poly. Oh, you mean the exponent?
No, just like the quasi-polynomial size of the adversary and the advantage.
No. So we assume that.
Wait, it should be size of the adversary to some constant, right?
Yeah, it's different, they're different quasi-polys. Yeah.
They're allowed to be different quasi-polys. But they're not, so.
Polynomial speedup that you allow, but not more than.
Wait, no.
No. I think we need that, sorry, so this is misleading, let me clarify it. We assume that there isn't a super polynomial speedup.
Yeah.
Sorry, never mind.
Yes.
Wait, Guy, you assume that there exists a constant C, big, so that any t-time adversary where t is quasi-poly
Succeeds with probability t to the c over 2 to the kappa. And this is directly inherited, so that's a corollary through this work with Canetti et al., where we essentially show that under these types of assumptions, the Fiat-Shamir transformation is secure when applied to interactive proof systems or certain types of interactive proof systems. Okay, so those are the two main results. And what I want to do, the main thing I want to do is talk about, in the time I have, is kind of talk about the structure of the result or how one obtains such a result. And if we have time, we'll sort of delve deeper into the sum check protocol and the algebra inside it. One thing I want to, given the theme for this week, I really want to dwell on the connection between proof systems and this class PPAD, which sort of characterizes, you think proof systems and kind of Nash equilibria, and these two things seem to have nothing to do with each other, but in fact, there's an interesting relationship when you're trying to show hardness results, and I think this is yet one more instance where proof systems end up having theoretical applications in areas where, at first glance, they really seem to have nothing to do with. One classical example is showing hardness of approximation. Here we have a different example for hardness on average, or hardness in PPAD. So first, when we talk about PPAD, we have this problem. We're given an exponential graph. We have a source, and we want to find a sink. Okay, and the first question, when I think about this as a complexity theoretician, well, p-space problems have a similar structure, right? We can think of a p-space, any polynomial space computation, as being represented by a graph, okay, where each node is sort of a possible configuration of the Turing machine. If it's a polynomial space Turing machine, then there's an exponential number of nodes in the graph. And what we know is we have the starting point of the computation, and we want to find the end point of the computation. Right? So that seems very similar to the end of the line problem, the complete problem in PPAD. And so why can't we use PPAD to solve? Why isn't it obvious that this is a hard class? And the point, exactly as was made here by David, is that when we're solving the end of the line program, no one guarantees. A solution isn't guaranteed to be the sink at the end of the line that starts at the source that we're given as input. Any source or any sink is a valid solution to the problem. So we might come with our p-space computation and ask for a solution, and we're going to get some junk node that's not on the computation path. It's not going to help us. Okay, so there are many solutions. Another problem is I said that in PPAD, or in the end of the line problem, we assume both that we can compute successors and also predecessors in the graph, whereas a standard computation only lets you compute successors. But using reversible computation on the results of Bennett, this ends up not being a big problem. The serious problem is that there are many solutions, and some of them might be much easier to find than the correct sink. So we don't think there's a reduction from p-space complete problems to PPAD. And this is where proof systems come in. And the idea is, well, what if we had a computation where what if we added proofs to these nodes in the graph? Okay, so what I want is for every node in the graph on the correct path, I want there to be a proof that it's on the correct path. And any node in the graph that doesn't have a correct proof becomes a self-loop. Okay, so if I had such proofs, then now I can build a graph where there are no sinks except the correct sink. And now, if you want to solve the end of the line problem, and I give you this source, you either have to cheat the proof system, okay, find some node that's not on the correct path, but somehow find an accepting proof for it so that it's not a self-loop, because self-loops are not valid solution, or you have to find the actual solution, and that's going to be hard because it's a p-space complete problem. So you're not going to be, or it's a hard problem. You're not going to be able to do that, so you have to cheat the proof system. And so basically we can use computationally sound proof systems, and what we're going to say is that solving the end of the line requires either breaking the proof system or solving this expensive computation. So that's kind of that's where proof systems come in and are really helpful for building hard instances for PPAD problems. Is that clear? It's a good point. It's a good time for a question.
But so far it's not clear why Fiat-Shamir matters, right? It's like Fiat-Shamir is one way to write down one thing.
Fiat-Shamir doesn't matter. So this is a general connection. Proof systems are helpful for PPAD. And I'll attribute this to Valiant. I don't know that it appeared explicitly, but this was Paul Valiant's suggestion.
So when you're sampling an instance, you're just going to think of every possible proof as a node, and then the proofs that would be rejected should become self-proofs?
Yes.
What was the question?
So could you repeat the question? So
I guess the general question was, what is actually the
instance? So the question was, what was the instance that we're sampling? And the instance is an instance for the original computation, this thing where finding the correct end of the path is hard. So I assume that's sort of hard on average, and I sample an instance for that. And then I also sample, I guess, public parameters for a proof system. And now every node on the graph contains a state and also a proof that that state is the correct state along the path. And finding a solution is either finding a cheating proof or finding the correct source. So that all sounds great. It's not as easy as it sounds, and it actually gets quite hairy. There's a reason we haven't had, this is a paradigm proposed by Paul Valiant in 2004, and we haven't really been able to instantiate it since then. And the reason is that we need really powerful proof systems. So one thing we need is we need to be able to move along this graph. Remember, we need to be able to compute the successor to any node, and that means we need the proof to be incremental. So given a correct proof for this state, we need to be able to hop along to the next state in the computation, and in polynomial time, quickly generate a proof for the next state along the computation. That's known as an incrementally verifiable proof system. It's not clear. I mean, that seems like a helpful object, and we're going to talk about it in a minute. But just any old proof system you pull out of a box, including Fiat-Shamir, is not going to have that property. A second subtle point is that we also want unambiguous proofs. To keep this nice structure, I want there to be a unique correct proof for every node along the path. I don't want to start having multiple nodes along the path because I want to keep the in degree and out degree to be at most 1. So we need what are known as unambiguous proofs. For every correct state along the path, there's a unique accepting proof, and it's hard to find. Maybe there are other accepting proofs, but it's hard to find them.
But why would 2 proofs be a problem? You're saying 2 proofs for 2 different edges is a problem?
Yeah, 2 proofs give you 2 different nodes, and now I don't know how the graph starts looking, and I'm worried. Yeah.
So your reduction works with any such proof? Your reduction works with any
I'll say it's valiance reduction, but yes, it works with any such proof system.
So basically your work by basically building this proof.
Yes. The main contribution is building such a proof system for a hard problem.
So maybe you could kind of think that in hindsight that Fiat-Shamir kind of gives you something like this, in the sense that Fiat-Shamir kind of forces the prover, even though it only gives you one message, to actually sort of in its head sort of step through this sort of interactive process. So, again, even though the prover is sort of doing things in one shot, then you have a way to sort of verify that it sort of goes through specific steps that are indicated by the interactive proof that you're compressing. So
you're talking about the unambiguous property.
Not with the unambiguous.
Or the
Why would you think that Fiat-Shamir would be useful for this sort of thing, right? So I mean, it's kind of it's not very accurate, but it does sort of have to. You could sort of describe it as having the flavor as sort of forcing a prover to go through like a sequence of sort of pre-designed steps in order to produce some output.
It's not clear that it's incremental. I mean,
yeah, it's not clear to me, but I think it's a nice. So here's a suggestion for. It's not an open problem session, but find properties of the original proof system that guarantee that once you apply the Fiat-Shamir to it, you get an incremental proof system. Kind of try to abstract that. It's not going to work, I think, for any proof system you start with, but maybe find some properties.
If we're talking about, it's a thing, but I think Fiat-Shamir it's obviously connected via Nash, right? They're both about finding the hardest of finding fixed point, right? So that's this, the hardest of codes, and obviously they're related.
Interesting. So, no, but I don't know how to make this.
Well, you are through.
Yes, I don't know how to make that. This is a very intuitive statement, but I don't know. I have to go like this to sort of back it up. Okay. Good. So kind of that's a template, and really what we want is, oh, yeah.
Does it also become a problem that the verification doesn't, or that with some probability the adversary can create a cheating proof, or do we care about the fact that it is statistical?
So we definitely care about it, and that's why we say that solving this graph requires either solving the original problem or finding a cheating proof. And assuming that the proof system is computationally sound, finding a cheating proof is hard, and so solving this problem will be hard.
If the proof system is hard, then sometimes the adversary gets very lucky and finds the cheat.
Oh, so we're just going to show, yeah, so I'm not interested, what I want to show is that the adversary can't succeed with high probability. Okay, so if he succeeds with negligible probability, that's fine. As always, when we talk about kind of hard problems, we allow a negligible success probability. No. Okay, so I want to dwell basically, as if that was saying, the main, really what we're talking about here is finding a hard computation where we are able to sort of have these incremental proofs. And that's interesting for showing hardness of PPAD, but I think it's a natural and interesting notion in its own right. It's incrementally verifiable computation, where what we're looking for, where what we would like is given a long computation, we want to be able to perform it via a sequence of small steps, polynomial time or maybe even linear time steps, where after every step we end up with a state. So after the ith step, we end up with the state sigma I. Okay, so we have this step or successor function, S, and we have a verification. So this state includes kind of the state of the computation and also a proof. And the verification given I and a claimed state can accept or reject. And what we want, completeness means that if we run this step function really L times, we'll get the correct output. But we want that at every step along the way, we can also verify that we're at the right location, even before we reach the end of the computation. Okay, so it's hard to find any state sigma I that will make the verifier accept that's not the correct one. That's the notion of an incrementally verifiable computation, especially I think for the workshop this week, is a natural notion to sort of dwell on. We have some examples along these lines. I'll talk about it at the end. We have very few, and I think it's a nice challenge for this community to come up with more. The point for the talk today and the connection to PPAD is that an incrementally verifiable computation procedure for any hard-on-average problem, using the reduction we just saw, immediately gives a hard-on-average distribution in PPAD, also in CLS. Yes, I need unambiguity. Thanks.
So is this requirement of unambiguity what makes it difficult to just take any like snark and construct IBC from it?
Yes.
We know through proof trees that you can extend it to any polynomial length.
But it's not unambiguous.
So I see. So if there were somehow some generic techniques that would give you snarks that are unambiguous, then potentially one could relax the assumption to just the existence of some, as opposed to talking about a particular subject.
Quite possibly, yeah. Okay. So I want to talk a little bit about how what we actually do is we build an incrementally verifiable computation for a particular hard problem. And that problem is sharp SAT, the sharp counting SAT problem, given a SAT formula on n variables, counting the number of satisfying assignments. Okay, so that's certainly NP hard. In fact, it's in sharp P, so it's a sharp P complete problem. We believe that it's hard. We know that we have a worst case to average case reduction from it, so we also know how to sample average case hard instances for which it's hard to count the number of satisfying assignments. And what the main contribution, or what we do, is we build an incrementally verifiable counter for this problem. Okay, so the way it looks is, we have along the way, we have these nodes. What we want is something along the lines where in every node along the way, it's not quite what we get, but it's close to it. So at every node along the way, we know the number of satisfying assignments up to that node. Okay, so in the ith node, we have the number of satisfying assignments sort of between 0 to the n and I, where I is a number between 0 and 2 to the n minus 1. And we have a proof that yi is correct. Okay, that's a correct number of satisfying assignments. That's the goal, or what we would want, is an incrementally verifiable computation procedure that just goes along and computes in the end the correct number of satisfying assignments for the formula, and also gives us a proof that that's the correct number. And if we can build such a thing, then we know that PPAD is hard. Good. Yeah, that's just the soundest condition. So how would we go about building such a thing, or what are the challenges? So first, we want polynomial size proofs. So I want a proof here that yi is the correct number of accepting assignments within the first I assignments. Okay, so we want a polynomial size proofs because we want each node to have a polynomial size label. And for that, we can use the famous sum check protocol of Loon, Fortnow, Karloff, and Nissan. That's exactly why it was proposed. It's an interactive protocol for proving that the number of satisfying assignments to a formula, either within a range or within all the possible assignments, equals some value y. Okay? But that's an interactive protocol. Okay, whereas here we have no interaction. We just want a proof, a non-interactive proof, and that's where we use the Fiat-Shamir transform. Okay, so using the Fiat-Shamir transform on the sum check protocol gives us these non-interactive proofs that are verifiable in polynomial time, showing that the number of satisfying assignments really is the claimed y.
Right. So the reason your result is about the Fiat-Shamir transform on the sum check protocol is this line, right? You do not any non-interactive proof would go because you need. I'm giving myself a sanity check. You need a proof that gives you a short proof for a big problem, and that's where the sum check protocol comes in.
Right, but I think that in general, I think of proof systems as, in general, giving a, proof system is interesting if it gives a short proof for a complex problem. So I would say any proof system that's interesting, you could plug in here.
Any proof system that has that property is just that we only know the sum check.
Right, right, and I think the main sum check and Fiat-Shamir are really important. So Fiat-Shamir is a way to make things non-interactive. That does seem inherent. But also we want this incremental thing. right? We want it to be incrementally updatable. And that I have no idea how to do for general proof systems, but particularly for the sum check, with the Fiat-Shamir applied to the sum check, we know how to do that. To get the incremental proof update, that's the main challenge.
Will you define an ambiguity in this context?
Unambiguity means that so first it says there's a correct proof for any step. And the second thing is that it's hard to find, even for a correct state, it's hard to find any accepting proof that's not the correct one, the prescribed one. Okay, so our main challenge is how in the world do we go from a proof that, within the first I assignments there are yi accepting statements to a proof that within the, this should be I plus 1, that within the first I plus 1 statements, the number of satisfying assignments is something. That's the challenge, and how do we do it? So the approach, the way we're going to do it is recursive, and so long as you don't care about bounding your proof size, it's very easy. So, but let's see the naive approach anyway. So suppose we have a counter, an incrementally verifiable counting procedure for formulas on j variables. Okay, so finding the number of satisfying assignments on j variables is sort of a problem whose complexity is size 2 to the j. And I want recursively to find from such a counter for counting the number of satisfying assignments on j plus 1 variables. That's going to be the approach. That seems, we like recursion. That's nice. So suppose we have such a thing for instances of length 2 to the j. This is this Lj. This is the length of the path of the incrementally verifiable computation. With steps, Lj steps, and it arrives at the correct solution and a proof for that solution. Yeah.
What's the arity of phi here? Or are these two different phis?
So yeah, these are two different phis. So this is the phi. This is a phi that has j variables, and this is a formula that has j plus 1 variables. So I want to, using a counter that can count for formulas with j variables, I want to recursively build a counter for j plus 1 variables, a harder problem. Good, and I just want to say that I don't assume here the length can be, I don't really care how this was done. Maybe it's a path of length larger than 2 to the j. Maybe there were some auxiliary steps here in the middle. I don't care. What I care about is that in the end of the day, there were Lj steps taken to do counting for j variables. And there's some proof in the end. There's a convincing proof. Maybe it has many sum check proofs inside it. Maybe it just has one. Maybe it's, I don't care what the format of it is. It's something, it's a convincing proof for j variables. Okay, so now what I want to do is I want to do j plus 1 variables. And the natural solution is, well, let's first count all of the assignments that end with 0, the number of accepting assignments that end with 0. And then let's count the accepting assignments that end with 1. And the sum of these two counts is the number of accepting assignments, right? Every assignment either ends with a 0 or ends with a 1. So that seems great. I can just do this counting, and then I can do this counting. But it's not as simple as it looks. And the point is that I can't forget, while I'm counting over here, the assignments on the right side. If we think about this as a recursion, while I'm counting on the right side, I can't forget the answer for the solutions that end with 0, and I can't forget the proof. Okay, so I have to keep that in my memory, okay, if I want it to be incrementally verifiable. So that in the end, I can actually compute the sum, the correct number of, the sum of these two values, and the proof of this sum is going to have in it embedded the proof for the first half and the proof for the second half concatenated. And then it's verifiable. Anyone can go and verify that in the left side, sort of by recursively, in the left side, there were really this number of satisfying assignments. On the right side, there were this number of satisfying assignments, and we are convinced. The problem is that winding this recursion, well, the number of steps we took is fine, right? We just sort of doubled, we doubled the size of the computation, and we doubled the number of steps we took. So that's fine. That seems fair. The problem is that we also doubled the proof size in the end. Okay, so if we do this, in the end, we're going to end up with an exponential proof size. That's no good. Okay, we want to end up with polynomial proofs. So this is a problem. It was also a problem that Valiant thought about when we was thinking about these things. And his solution was to say, well, let's take these proofs and merge them. Okay, so let's take these two proofs and add an extra node that sort of merges them together into a new proof that proves the sum, and then we'll be okay. Okay, then we've sort of shrunk the proof back down to size, and we can move on in the recursion. Nothing is going to explode exponentially. So that's great if you can do it, if you can merge in polynomial time. That really does work out very nicely. The problem is that this is hard to do. It requires super extractable snarks in Paul Valian's work. It's hard to see how to do it, or I don't know how to do it, with an unambiguous proof system. So it seems sort of inherent to these super extractable snarks that use CS proofs. Ambiguity seems inherent, so it's not clear how to use this idea. It's nice if you just want to do incrementally verifiable computation as an application, but if you want to use it in order to get unambiguous proofs and show hardness of PPAD, it's not clear what to do. Okay. So the new idea, or the way we take it on, is we do this recursion, we do the left half and we do the right half, and we end up with these two proofs, and we'll merge them. The point is, this merge doesn't have to be sort of a single step. Maybe it can be a long computation, so long as the merge itself is incrementally verifiable. Okay? So we're not going to merge this in one step. Instead, we're going to take a possibly long path. Maybe it's a constant, even a constant number of times. Maybe it's 100 times the length of the left side and the right side. We don't care. So long as this path in itself is incrementally verifiable. This merge itself is incrementally verifiable, right? We want everything to be incrementally verifiable. So even in some intermediate node here along the merge computation, I have to know that I'm in the right place and I'm doing the right things. And then in the end, we'll end up with one merged proof. And then we're good to go. We've shrunk the proof size down, and nothing explodes. Okay, so that's the idea. Of course, the question is, how can you do it? But on a conceptual level, one new idea is that rather than merging in one step, you can take a lot of time to merge. Not too long, but a long time, so long as your merge itself is incrementally verifiable.
So, sorry, so gotcha, long you mean, so...
so I think about it as a constant number of times the length of sort of the counter for j variables.
Right, so, but to go for one step and you need to be able to verify it in polynomial time.
Yeah.
The L can be exponential.
Yep.
So that will allow you.
So we have an exponential number of steps here. Each of them is polynomial. And each of them, once you get to it, you can verify, anyone can verify that you're in the right place.
So you're allowing the merge to take a really long time to do.
We're allowing the merge to take a really long time, and that's sort of key. And that's exactly where, going back to Zvika's point, since I'm not going to have time to show I can do it, maybe we'll end, and everyone can go get some wine in the reception, and then we can come back and do kind of the algebra of the sum check and show how we do it. But that is where we really, really use the structure of the Fiat-Shamir transformation and the structure in particular of the sum check protocol in order to merge sum check proofs. So I have this dramatic slide, but I think we're not going to go into the belly of the beast. Bye. I can sense the disappointment now. Okay, so let me summarize, and then maybe we can discuss. We had good discussion during the talk, but we can discuss some more. So summary, there's this rich complexity zoo between NP and P. We as cryptographers are used to thinking about the cryptographic problems between P and NP. We know classes like SZK, statistical zero knowledge, the intersection of NP and co-NP, but there's a whole other rich complexity zoo that some cryptographers have been working and making very beautiful progress on, but I think there are a lot of open questions and directions to pursue by taking the cryptographic lens to exploring complexity here. We have this notion of incrementally verifiable computation that I think is really interesting in its own right, and once we add the unambiguity property, leads us to hard problems in PPAD. And we instantiated this sort of general connection, specifically using the Fiat-Shamir for sum check to get an incrementally verifiable counter for counting SAT. Some open problems, so just this notion of incrementally verifiable computation. More schemes for more computations. I just think it's a nice problem that is underexplored. We have some upcoming work on that with Omer Panet and Moninor. I meant to put up a citation, but forgot. This question of instantiating the Fiat-Shamir for SumCheck and other protocols, Alex will talk about it. I think it's a fantastic open problem. Maybe it can lead to hardness or to showing that, something like the LWE problem is in PPAD or factoring is in PPAD. And there's a couple of recent works replacing the sharp SAT problem with a repeated squaring problem that's related to the hardness of factoring. And I think finally, sampling small, hard instances of Nash, actually being able to sample these games. There are a couple of bottlenecks. There's a question of the reduction from the end of the line problem back to the Nash equilibrium problem. There's some work on that in the game theory community. And from our side, coming up with these very succinct, small instances of the end of the line, nice instances of the end of the line problem is a nice direction. And I will end there. Thank you.
I have one question. So going back to the question about would the snark that is an ambiguous suffice? So still not, right? Because the line would be exponential in length, and even if I build proof trees with hierarchy, they would only suffice for an arbitrary polynomial, but not for an exponential length line.
You'll have to do some leveraging. You don't have to have the line be exponential. It'll just be slightly superplanar.
I think it depends on what's happening in your extractable snark and kind of the assumption in there.
Because in the after volumes work, there was, we do understand these things better than we did back then. In particular, we know how in the recursive extraction behaves a little bit more carefully, and we can prove it from not super extractable snarks for any polynomial length computation precisely by using hierarchy trees. But maybe with complexity leveraging good enough, and maybe this ends up being just getting an ambiguous snarks as the main barrier.
There's also a question of confidence. I think a lot of what this line of research is about getting more concrete evidence for hardness of Nash, and maybe for practically, heuristically understanding the security of snarks, then we're okay with knowledge assumptions and we're okay with Fiat-Shamir heuristics, but here it's not clear that, snarks will give you maybe an alternative assumption, but maybe not a good assumption to base.
Conversely, this unambiguous property, so it's inherited by the reduction, right? So, but one could maybe think of, is there any hope to get rid of it? And
so I think that's a great open problem is the unambiguity seems sort of important if you want to make, so let me go back to that picture. Where is that picture? Here it is. Right, so we use a proof system to sort of make all of these guys self-loops and keep the original line as just a line, and that's where we needed the unambiguity. And I don't know. I think it's very interesting to ask if you don't have unambiguity, but you do have a proof system that's incrementally verifiable, you end up with all of these extra nodes along the path, and you somehow need to manage things so that there are no collisions. It's not clear that you can't. In particular, if there are sort of two proofs for every statement, but the two proofs are unrelated and they just form two lines here, then you're fine. The problem is what happens if things start colliding and diverging, and how do you control the structure? But I think it's a good open problem. I'm not pessimistic about it.
There's also this Bennett reduction hiding there for making this path reversible. And in this case, if you have a proof that's not unambiguous, then you'll have a concrete attack. You'll have very easy nodes, very easy sinks in any such graph, no matter what problem you start with. Bennett's reduction will manifest.
So I think it depends. All I want to say is that it depends on the proof system, right? If the proof system somehow, if it's ambiguous, but it sort of just generates with the successor and the predecessor, it generates two separate lines, then I think you might.
If yours the last bit of the proof, then once you go through this reversible computation reduction, which will correspond to these two parallel lines, then the reversible computation reduction will make a graph that's full of sinks.
So I don't disagree with you. I'm just saying that the fact that a proof system is ambiguous doesn't on its own mean that this reduction fails. Okay? So there might be an ambiguous proof system where you can make it work.
So are there any more instances where we use unambiguity of proof systems for good?
So Yeah, so in particular, Ron and I have some, so we use it for batch verification. It's very helpful for batch verification. So the property, if you have a proof system, an interactive proof system that's unambiguous, even a non-interactive one, then that's very helpful for batching many verifications, kind of verifying K statements at much less than K overhead. And I don't know, that's one very nice use of it. Yeah.
Statistical soundness.
Statistical soundness, I think maybe you could get something like that also for computational. Just for computational, we already know batch verification results that go in other directions. And I don't know other applications for unambiguity. There might be ones.
So in the open problem slide, you talked about Fiat-Shamir for the sum check protocol, but like you have to define exactly what you mean. So sum check, like the prover is not efficient, and after Fiat-Shamir you have like an argument, right? And you don't allow the prover to be more than polynomial time, but the honest prover is the one in.
So there's an issue of the running time of the honest prover, and in these results we have for instantiating the Fiat-Shamir, the running time of the honest prover in the protocol plays an important role. And you can think of various ways around it. I'm interested in instantiating it for sum checks of polynomial size, and I assume that through some complexity leveraging that will give a result for PPAD. But you could also think of instantiating it for other problems where maybe they're using a trapdoor, the computation of the prover can be made more efficient, which is a nice direction to go in.
The honest prover is running in quasi-poly time? Like,
in the hard instance we build, the honest prover is running in quasi-poly time. But the proof system is sound until against much stronger provers. There's some complexity leveraging going on.
Yeah, I just wanted to ask, so if I understand correctly, your merge operation is like every move that you do is efficient, but you're not actually efficiently merging two useful computations, right? Like your sum check ending at 0 and sum check ending at 1, you're not efficiently merging those.
I mean, so the question was that we're not actually we have this long merge procedure and every step along the way is polynomial, but we're not actually merging two useful computations efficiently. And that's right, we're not merging them efficiently, we're taking a long detour to merge them. And in particular, what this means is that we end up, if we just think about this as an incrementally verifiable computation scheme, it has a big overhead, right? There are many steps along the incrementally verifiable computations that don't really correspond to helpful steps along the original computation. So it's a big detour you're taking in order to get this verifiability along the way.
Okay, so if there's no more questions, let's thank Guy again.
There's a reception, right?
Correct.